Dr. Jones.
Thank you. Thank you. Thank you for having me here today. I just must start by saying this, that you are so lucky, all of you who studies here. I've had a day filled from 9 o'clock where I've met with your professors, and the variety of the things you do here and the opportunities you are lucky to have, and make sure that you take advantage of it. First, some quick facts about Sweden. So we are based here, Northern Europe. We're a quite long country, as you can see. If you put a pin down here and spin us around, we will touch Italy. So we have a spread that is quite long from north to south. However, compared to you, we're only 10 million people, and 2.3 of those millions have foreign background. It has about 450 square kilometers, and just because I have an American audience, I have translated this into square miles so that you will know. We have a quite low density of 22 inhabitants per square kilometer, 57 per square mile. 85% of our population live in urban areas, and our main energy sources are hydropower and nuclear power. However, we have other energy sources such as wind power, solar power, biofuel, and waste combustion, whereas waste combustion is what I will talk to you about today. Other important facts about Sweden, you can see our demographics here, the density. As you can see, not many people live in the northern part, density 10 or below, whereas our main area here, Stockholm, which is our capital, has a higher density. Also the Gothenburg region, which is the region I come from, has a high density, and then the southern part. So we do have a lot of land that could be considered unused, but it's actually high quality forest in this land, and we make a lot of money on our forest. So we don't predominantly do biomass combustion, even if we would have the possibility, but the quality is too high to actually only combust it. Also, some other facts about Sweden. Could anyone guess what's the most common Friday evening meal in Sweden is? What do everyone eat on Friday evening while watching TV? Tacos! Yeah. So, see, there's a lot of things you don't know about Sweden. So kind of the way that you in the English-speaking world refer to keeping up with the Joneses, with the Jones being like the average person or a middle-income person, we have the same. We say the Svenssons, and this is the typical Svensson meal. The Svenssons will have tacos on Friday evening. So RISE, then, the company that I work for, some quick facts. It's a non-profit organization. We are owned by the Swedish government, and we are meant to be neutral in all our research and everything we do. We have offices all over Sweden. Our main office is in the city where I was born, correctly pronounced Borås. It's not the city where I live, but I drive there into my office every day. We do have some presence in other countries. We do have a fire lab, not combustion, fire, so uncontrolled fire labs in Norway, where they look at like tunnel fires, wildfires, and things like that. So there we have presence in Norway. We have some random people like myself. I now live in Toronto, Canada. I have a research project going on there, and we have some presence in the States as well. But out of our 2,200 employees, the majority are placed in Sweden. 30% of the people working for us have a PhD degree. We also have some people that are professors at universities at the same time as they're working for us. We are supposed to be the bridge between academia and industry in Sweden, so that we're supposed to help facilitate the exchange of research between the two. Our turnover was approximately 2.5 billion Swedish crowns. The Swedish crown is, so you take 10 crowns to the dollar approximately in 2016. We are non-profit, as I mentioned, which means that if we make any more money than we have budgeted for, it's invested back into our organization. We buy new facilities, we employ new people, etc. We work quite a lot with small and medium enterprises, and they stand for 30% of what we have as a turnover. And we have over 100 test and demonstration facilities. These are open for industry and for universities. We work together with SMEs, as I said, and we are the owner or partner in 60% of all the testing and demonstration facilities present in Sweden. Back to the fun stuff. So, the title for this, How Combustion Became a Success Story for Swedish Waste Management. You're going to notice during this presentation that I'm going to give you some general facts about Swedish waste management, and you can then reflect back to how you see your everyday life here in the States and see what you think the difference will be. So, the Swedish waste history then. In the late 19th century, we had a cholera epidemic, and it accelerated the startup of municipal solid waste management because people started to realize that we cannot just throw our stuff on the ground anymore. We have to move it away from the city. So they started thinking about how can we facilitate this, because they also noticed that even if we do put it outside of the city, we're kind of creating a mountain already back then. Someone had a great idea. Let's use pigs. We can let the pigs eat all the waste, and then we can eat the pigs. Turned out that wasn't a very good idea. Apparently pigs can get sick from waste, and apparently eating a sick pig is not very good for a person either. So actually in 1907, Sweden started its first waste combustion plant in operation. I say waste combustion, which isn't entirely true. I would consider this one to be an incineration plant, and that's the word that you are more commonly familiar with using when we're talking about waste. In an incineration plant, it's about devolumizing. We just want to make it disappear. We don't really care about what comes out of it. Today, we have combustion facilities. We produce energy and we produce heat and electricity from these facilities. Therefore, we're trying to avoid the word incineration because it has a little bit of a negative tone. So we say waste combustion now. In the 1950s, we continued on the development of the district heating system in Sweden. So are you familiar with the district heating system? Pipes under the ground, spreading out low quality heat so that you can heat up houses. You can connect to this system and actually use it for district cooling. Hospitals can connect and actually cool facilities with it. We started in the 40s, but then after the Second World War it really took off and we built out our district heating system. And then the 70s and the 80s came. There was a worldwide oil crisis. You can just imagine how that affects a country that have no oil or no other fossil resources. What to do? Well, we have this waste here that we're just getting rid of and devolumizing. Maybe we can connect our waste facilities to our district heating system and we can make heat out of it. Great idea. It worked and it's still working. I would say that the last 30 years have been the most important for waste combustion in Sweden, and it has to do with a lot of political drivers. I won't go through all of them, but what I want to point out is that you see that in 2000 we introduced a landfilling tax. It was followed up by a landfilling ban on combustible waste, and in 2005 there was also a landfill ban on all organic waste. And these are not only applicable to Sweden. This is for every member state in the European Union. And at the moment there are 28 member states in the European Union. You're all aware that one of them is trying to leave. But we all have the same regulation, which means that nothing that can be combusted and nothing that is a food waste is supposed to go to a landfill. It's a little bit different here. You still landfill the majority of your waste. We kept on increasing the landfill tax as this happened. We did introduce an incineration tax on household waste in 2006. It only survived 4 years before they realized that together with these ban, it's ridiculous because we're actually producing energy. The most recent ones that we've had have been the waste prevention programs established, and this is a framework directive also from the European Commission. And it's also a demand that there has to be separate collection of paper, metal, plastic and glass in all European member states by 2015. We had this pretty much sorted out in the 90s in Sweden, so we're good to go there. The upcoming goals that we have is to have at least 50% of the food waste separated and 40% have to be used to recover energy. We will clear that goal next year when we hit 2018. The EU has decided that by 2020 the greenhouse gases are to be reduced by 20% compared to the levels of 1990. We were already there, so we decided when this goal came out that we're going to reduce ours by 40% compared to 1990. By 2020, we also have to have sorted out 50% of the total amount of paper, metal, plastic, and glass. It has to be reused or recycled. And by 2020, we also have to reuse or recycle 70% of the construction and demolition waste that is created. So 4 decades of work then. If you would divide the waste management and how we treated it back in 1976, it would look like this. Sweden produced 2.6 million tons of waste. 62% of it went to landfills, 30% went to combustion, and then we had some recycling and some biological treatment. 2016, it says 1%, but it's actually lying because I wanted round numbers, but it's 0.7% of the municipal solid waste that goes to landfills in Sweden. 48% is used for energy recovery through combustion. We have 16% biological treatment of the food waste and garden waste. What we do is that we make biogas. It's used for vehicles, so any municipality that owns a facility will drive all their own trucks and their buses in the transportation system on biogas, but it's also fed into a biogas grid mixed with natural gas grid, so you can fuel your own car if you have a biogas car. And
what are the numbers for the US?
I don't have the numbers for the US. Yeah, what would we estimate? I would say that you would still be on a quite high level of landfilling. Yeah, yeah. As you can see, we have almost double the amount of waste that we produce. This is a problem for any Western country. We consume a lot today because we have money. There's nothing wrong with consumption because it's kind of what keeps our countries going. But we as consumers should be more aware of what we consume, and we should put pressures on producers to make sure that what we buy will be reusable or recyclable. So that's something that I want you all to bring home with you. And if we look at this graph, we can see how it's been developing over the years, how the landfill went down, then we had a bit of a hiccup here, but then it's continued to go down, and now it's reached a kind of a stable level of less than 1%. The energy recovery has gone up, but also the material cycling, which is of great importance. So the latest trend, and this is something that I'm quite happy about, considering what I just mentioned, is that in 2015 we had 4.7 million tons, and in 2016 we had 4.67 million tons. And this means that we have gone down from 478 kilos per person to 467 kilos per person, which is important because this is the trend that we need to see. We have to reduce what we use so that we will put less pressure on the environment. So to make a summary of all of this, one could say that from 1990 and prior to this, the waste system was based on a landfill economy, and there was a small part of waste-to-energy facilities. And the consequences of this was that it was a large environmental problem because landfills, they cause emissions of harmful greenhouse gases. They emit methane, which is a worse gas in the atmosphere than carbon dioxide. And there is also a risk of leakage of leachates down in the groundwater. So you could actually also pollute the water in areas where you have landfills. And the characteristics and the public opinion is that waste is a problem. But from 2005 and on, we have a diverse system with many different treatment techniques. We have the reuse, we recycle, we have biological treatment, and we have our waste to energy, where we produce heat and electricity. So the waste sector is now a resource base. We have material and energy, and we have biogas and fertilizers from biological treatment. So it has instead turned into an industrial sector, and suddenly waste is valuable, and it's now something that people are arguing over at some points. So the political aspects then, on a national level, to be able to pull something like this off, is that you have to have committed politicians. We change our government every 4 years in Sweden, but all our environmental goals are pretty much the same. So no matter who is running the country, they will work toward the environmental goals, and this is partly facilitated by the fact that we have to, as a member state, respond to EU's goal lines that they have set up for us. So on a national level, there will be legislation, national environmental targets, a national waste plan, and different guidelines that's provided by the government. And on the local and municipal level, there is a monopoly for household waste for municipalities, which means not only that they have the right to it, but they also have to take care of it. which requires them to have local waste plans and local regulations. Not all municipalities in Sweden have the possibility to have a waste combustion site. Of course, they're expensive investment, but with transport and with municipalities going together and building together, we've solved it quite nicely. So before we go into the combustion, I just want to talk about how we clean out recyclables from our combustible waste at source. If I've understood it correctly, in Utah you have the version where you have one bin where you put all your recyclables, correct? Yes, you agree? So in Sweden we have to divide it at household level into plastic, sometimes soft plastic and hard plastic, colored glass, not colored glass, metal, paper, newspaper, boxes, everything. You have to do that yourself. And if you live in a larger city or like in a condo complex, apartments, then you will most likely sort it and then walk up to 0.5 kilometers, 500 meters, which would be something in miles. You have to convert that one yourself, to a recycling station where you put all of these things. If you happen to have hazardous material like leftover paint or aerosol cans or electric waste or something like that, you have to take it to a recycling central, and there are less. There, in a big city, maybe you would have 3 or 4 of them. However, it's normally free to go there a limited number of times per year. It's anything between 6 or 10 times, and this is because this is for the private sector. So to stop smaller companies from being able to go there and dump their waste, you have a limited number of times you will go there. But really, how often do you have to throw out a computer? It's not that often, I hope. Depends on how angry you are when you're studying for midterms, I guess. But there are also more and more places that offers at-home recycling, which means that you have a waste room in the apartment building where you live, where you can do all the sorting. So I asked my sister, she lives in Stockholm, Sweden's capital, to take a photo of what it looks like where she goes. She has to walk about 200 meters and she gets to this place. And then she has newspapers and plastic and metal and glass, and she has her little bags and she sorts them. This works fine for her. She's 35. It's not a very good system if you're 95. You have to carry everything out. So therefore we're trying to make it more user-friendly. My dad lives on the countryside, and when I say countryside, I mean a village, 600 people. From our house you can see no other house. He has 20 kilometers. You have to do that one too, to the closest city. And before he had to do all the recycling at home, he could only throw away his combustible waste in his bin, and he had to bring his recycle with him when he went into town to buy food. So first he went to did the recycling for what he had kept for the last week, and then he went to get food. Now he has these 2 bins, and when he opens them it looks like this. So he will be able to sort into 8 different fractions at home. This is easy, and it provides the recycling centers with a very clean fraction, if done right. But obviously I've trained my dad, because I cannot have dad fail when I'm in this field. And there is also a small little extra container that he can hang on the outside if necessary, that take light bulbs and batteries. So he can get rid of his some of his hazardous components this way as well. So this puts some pressure on people in Sweden on the individual level to actually do something right for us to be able to get only the combustible part, because we don't want the recyclables in there. So obviously always when it comes down to a personal level, it's going to be harder to get everyone involved, but we're doing okay. I think there is always room for improvement, but so far it's going well. So one step on the way, I call this slide, and I do that because in the European Union we are working towards something that is called the waste hierarchy, and it starts down here with landfilling, and then you have energy recovery, recycling, reusing and reducing. And this is what they base all their guidelines on. So this is what the whole European Union have to work at getting up, and it's sometimes it's shown as a stair like this. I like the stairway because I'm thinking that it's a tough climb, but when we come up to the top it's going to be a beautiful view, because it will be less waste and everyone will be happy. And one step on the way is then energy recovery, stepping one step up from the landfills and instead using it to produce energy. We have 34 plants in Sweden in total, and they use 5.2 million tons of waste, and 2.3 million tons of this is municipal waste, and 0.8 of these waste is imported waste, and I will get back to that later. The gate fee average is just under 40 USD per ton, and they are mainly municipally owned. A few are intermunicipal waste companies, but mostly they're publicly owned energy companies. And we have a few of them that are privately owned. You will see on several of my slides that I'm referring to a source that is named Avfall Sverige. This is the Waste Management Association of Sweden. They have done a great job in getting all the municipalities to work together. So even though in some areas there will be things that they don't want to talk about, they have a database where everybody can put their statistics in, so we can follow the waste for all of Sweden. And it's a good way to collect municipalities to be able to find research topics. What's important for you in municipality now? Oh, it's the same in this municipality. Maybe we should do research project together. You will learn from each other. How's your ash handling system? No, it doesn't work well. Have you tried this? Etc. etc. So, are you familiar with boilers? Yeah, a little bit. I see some nods. Yeah. So we use boilers for waste to energy to convert the fuel to residential district heating or cooling. It can also be used directly in processes, especially for the plants that are built in industrial areas where the steam can be directly used by another company. And there is also power production. The waste is collected and it comes to the facilities. There will always be some kind of pre-treatment and recovery of material. There will always be someone who's put metal, even though it should have been recycled, and metal is easy to get out, right? Because magnets and stuff like that. Then there is the actual combustion. Heat exchangers through a turbine making power, and then heat exchangers for district heating and cooling. We produce a lot of ash and slag, obviously, but less if you look at volume of what it would have been to put the waste in landfills. This will be post-treated. There will be a recovery of metals. So this is actually a way of getting metals back into the system to get new raw material. There is a huge cleaning system on a boiler. If you've had the opportunity to go to one, you will have seen this, that the actual place where the fire is a lot smaller than the cleaning facility. To make sure that the flue gas is clean, there are great limitations of what a flue gas from waste combustion can look like in the European Union, and obviously we follow them as well as we're in the European Union. And when you talk about waste combustion, a lot of people are scared of dioxins. There was a dioxin scare in the late 70s when they were discovered, and also how harmful it was and how much of quantity there was in waste combustion. But since then we've been able to take it down, and I could be wrong because I haven't looked since 2 years back, but the emission limit was 0.02 nanograms per normal cubic meter for flue gas, and we haven't had anything going over that in the combustion facilities. And they check it, by law they have to check it twice per year, but they do it themselves several times per year because you don't want to have that half-year checkup and realize that you have to shut down. So we're strict about that, which is good. We have two dominating techniques in Sweden. One is the grate-fired boilers that you're probably aware of. They can be a little bit of different design depending on how you have the fuel and the air coming in. We have co-current, counter-current, and cross-current. But generally it's a grate, a bed where fuel is fed in and air comes in, and then it goes in here to the heat exchanging areas, and then what would be here missing is the big cleaning facility for the flue gas. When you have a grate boiler, you can take basically the bag that someone throws out at their home and throw it directly on the fire. This means that you don't have to have a big pre-treatment, and we have done this for such a long time that it's an easy technique. It's about 70% of the plants that we have in Sweden use the grate fire technique, but it also means that you can have areas that are warmer than other because waste is extremely heterogeneous. I mean, think about your waste bag that you threw out last week. It will probably not look like the one that you threw out this week because it all changes the whole time. The other technique is the bubbling beds, the fluidized beds. We have two different. We have the bubbling fluidized bed, a sand bed, with where air is going in and it bubbles the bed so that you have a good heat exchange surface, or the circulating where the air actually is so vigorous so that particles will come with and then be introduced again into the system. To do this, you have to pre-treat your waste. Waste cannot be bigger than 10 centimeters, so it kind of requires you to have a facility where you can do the treatment, where you can mill it down to a certain size. It also opens up for you to be able to recover more material before you combust it, because you will find more material in that material that is being milled. But it's also, they both have different challenges. I mentioned earlier that we import fuel, and you can think about that while I take a sip of water. What does that mean? We don't have enough fuel in Sweden for our waste combustion sites. So the stuff that you put on landfill here today would work very well in our boilers, but it's a little bit too far between the States and Sweden to actually do that transport. But we have an overcapacity. A couple of years ago, when people started making plans for how they would develop the municipality and the energy companies, they saw the amount of waste and they looked at, oh, it's going to continue to go up. We will have more waste. No, because new regulations came, we got better and better at recycling. We're actually reducing how much waste we produce now. Waste is going down. Waste is used for other things. There was a European undercapacity, which means that as I mentioned, all the member states in the European Union have to follow the regulations, but they have no combustion facilities. They are in political situations where they cannot build because some politician says, why should we only build for the first step on the hierarchy? We should go to the top. We should reduce. It's a very nice thought, but how do you go from actually putting it on a pile to not having it at all? It's a quite long step. So this means that we could export our service of waste combustion to other European countries. We get paid to take the waste in, and the companies then get paid again when they sell the energy. So it's a win-win situation for the facilities. If you look at the monopoly of municipal waste that they have in Sweden, it's good because they know that they will have a steady income of waste, but they cannot say no to it. So when it comes to the imported waste, they can specify exactly what kind of waste that they will accept into the boilers. So what we've found is actually that the imported waste have a higher quality when it comes to like the heating value and the number of alkalis present in the fuel. Alkalis are problematic in combustion because together with chlorine they create deposits that are corrosive. So it's been good. As you can imagine, when the public finds out about other people dumping their waste on Sweden, this was not positive, but it's turned around now. We've been able to publicly describe and explain how this is actually beneficial. And one of the ways that I like to express it is that waste is not a local problem, it's a global problem. You've probably seen the reports of what's happening in our oceans, and you will have waste in the oceans around America's coasts that are not from America. So like this is global. So when we can take in waste and make energy out of it, instead of it being put on a pile on a landfill in another European country, the total sum of that is that we're doing the environment a favor. We're replacing fossil fuel in Sweden, and we're also replacing something that could have gone to a landfill in another country. I am quite good on time. So this was like the general background to waste combustion and what is the background to why I do what I do. Kind of a funny way of saying it. I wanted to present some of the research projects that I've done. I don't have super much time, so any questions, feel free to come with them afterwards. I'm going to describe 4 different areas within the waste combustion that I've been focusing on. The first one I will talk about is fuel characterization. This is what I did my PhD in. I did chemical characterization of solid fuel that goes to waste combustion. The importance is, as I mentioned, because in biomass you have a lot of potassium. And maybe you're aware of the fact that potassium chloride is corrosive to biomass boilers. Well, in waste we have a lot of potassium, we have a lot of sodium, and we have a lot of other players who wants to be involved in the corrosion and in the deposit formation. So it's very important to be able to have a picture of what the fuel looks like that you put into a boiler. So let's start with the fuel characterization. It's extremely challenging because the waste is heterogeneous. You will not have the same waste today as you had yesterday. You do not have the same waste in the summer as you do in the winter. We have done studies that has shown that apparently around Easter, everyone in Sweden cleans out their garage. Because you can see in the waste that you get more of the broken tire from bikes and things like that. When it comes to fuel characterization at grate-fired boilers, as I mentioned, the bags that you throw away, those are the bags that are fed from the bunker directly into the boiler. To take a representative sample from a bunker is extremely tough. And we have had to develop a method that is very time-consuming and very expensive to even be able to get something that would be a representative sample. I'll talk a little bit more about that later. At a bubbling bed or a circulating bed, it's a little bit easier because they pre-treat their waste, which means that it's mixed. And it also fed in often in a falling chute, which means that you can take samples from a falling stream, which is a lot easier than taking samples from a bunker. We do this to determine the fuel quality. Sometimes we have companies that come to us and say that we have problems with our ash feeding system, and we ask them, do you know how your fuel looks compared to what your boiler is manufactured for? And it turns out that because we're now reducing the volume, we're taking out more recyclables, we're taking out paper, we're taking out plastic, taking out the things that normally burns quite well. We're getting better and better to get out the food waste, so the fuel is drier than it used to be. All of this is important for the owners to know. We've done some mapping of the possible seasonal variations, as I mentioned earlier. And because we are looking at quality and want to look at quality over the whole year, all the time, we do a lot of education of the staff at these plants so that they know how to take representative samples. And also, when there are new boilers that are starting up, it's a way to get to know your boiler, to know your feedstock into the boiler. And as I mentioned, it's important to use it to evaluate the boiler performance compared to the contract. So these are some photos and drawings from a project that I did recently. This is actually one of the world's largest waste combustion facilities. It's fed through a line that takes the pre-treated waste, so it's already milled and quite nicely distributed, and it feeds it down to these 4 silos that then feeds it down into the boiler. When it was new, the owner and the manufacturer wanted to know, are they feeding the same way? Does the fuel meet the contract values, etc.? So we decided that we need to take samples from each silo to determine this. We manufactured this device to be able to do the sampling. You see, it's very glamorous. And this, what it was actually looked like. You would have wished that someone who manufactures a boiler and puts a hole to be able to take samples would actually also make it high enough for someone to stand up straight. This is not often the case. As you can see, this guy is now opening the hatch. There are things falling out, and it's a challenge to take fuel samples. One of the largest errors is obviously the human factor. We cannot have the same person take every sample every other hour for 24 hours for 3 weeks, because it would be illegal, and it would also be a very tired person. So you have to make sure that they're educated so that they're at least trying to do it the same way. And this is, as I said, this is the easy way to sample. In a grate-fired boiler, it's a lot more complicated. You have to, for several weeks, mix the fuel when it comes in. So you need the guy who is controlling the mechanical arm that feeds it into the boiler. You have to have him on board so that he mixes everything. Then you will take out a sample of 3 to 5 tons. You have to mill it, and then you have to spread it out on a big surface, take away half, spread it out again, take away half, do that 4 times, and then divide it into squares and take samples from each square. It's normally a day of at least 8 hours for 3 or 4 people. So it's extremely costly for the plants to use that method. The common parameters to look for in a fuel analysis for waste is the size distribution. It's important when it comes to like inert particles and things like that. They do a sorting analysis, and that means exactly what it sounds like. A person who looks, what kind of material is this? And you divide it into different, like glass and metal and plastic, etc. Sometimes they look at bulk density, net calorific value, of course, the initial ash deforming temperature, moisture and ash content. The metallic aluminum content has been more and more popular over the last years to look at, and then all sorts of different compounds as well. And what we do with it then, it would be very easy just to put this one up and then like say here, oh, we have this much chlorine, this much of this and this much of that. But it doesn't really give a visual, it doesn't really say anything, it's just numbers. So what we have decided to do when we have the kind of works like this is that we normalize the values. So we divide the values by the average for the full sampling, and we plot it on a logarithmic scale. So if you're on the line here 1, you are the same as the average. If you're up here, you're 10 times more, down here 10 times worse. This is an example from 2 different plants. It so happens to be that one of them is a grate fire and one of them is a bubbling fluidized bed. And here you can then see that the main elements, as we call the carbon and hydrogen and nitrogen, they're fairly stable. They're fairly the same, even in waste. But when it comes to like the trace metal, it's all over the place. Interestingly enough, in this study, was that if we looked at the waste composition for July, June, and August, when this particular plant 1, baled all of their industrial waste, because during the summer, of course, the heat demand goes down in Sweden. Even in Sweden, it gets warm enough in the summer. We could see that some of the parameters were constantly under the average. We plotted the same for the other plant, however, they closed their plant down in June, so we only have numbers for July and August here, but we don't see the same trend, even though they also bale their waste. So you can do studies like this, where you actually just look at the numbers without looking at the numbers, just to get a feel for how the boiler performs. These data are based on a year of samples, which means that we took 1 sample each month for both of the plants. Going into next example then, the fossil content in Swedish waste fuel. Often when we speak about waste combustion, we get a question about emissions, but you're creating carbon dioxide and it's bad for the environment, and why don't you think about that? Waste combustion in Sweden was the first to be introduced in the emission trading system, which means that they pay for the carbon dioxide equivalents that they release, and it's a trading system, so you only have a certain number that you can use. And before introducing this, the Swedish EPA wanted to know, because you are supposed to only pay for your fossil CO2 that you emit, so they wanted to know in waste how much is fossil. So we decided to do this study. We introduced it in the emission trading system after we actually completed this, and we did an evaluation with 4 different methods. We did sampling of solid fuel, and we did a carbon-14 analysis on that. No good labs in Europe, so we actually used a lab in Miami. Flue gas sampling, also with carbon-14 analysis, and we did calculations via a method called the balance method. It's a method developed at Vienna's university in Austria, and we also did a sorting analysis followed by modeling, and that's the old way we did it. So I did it for one of the plants. It took us, we were 6 persons, it took us a whole day. We opened 800 kilos of waste bags from people. Opened them and divided them into the material that they represented. And we did this at 7 different plants. 1, 2, 3, 4, 5, 6, 7. And the most southern one and the most northern one, it was 1,000 kilometers in between, about 620 miles, so that we could also represent this area up here where the population is lower. In total, we took 42 solid waste fuel samples from the 7 plants and 21 flue gas samples. We did 4 sorting analyses at separate plants, and we did 2 balance method calculations. As the balance method is a method that requires software, it's quite expensive. So we bought 1 license for 1 plant, and we were able to use old data from another one to calculate according to the balance method for the other plant. To also test this, we took 14 fossil-free samples from the plants, And by fossil-free, I meant that we went in and we actively chose things from the waste that we knew weren't fossil, like wood pieces and things like that. And that was a way for us to validate the lab in Miami that we used, so that we knew what we had sent to them. Turns out, I think, that this gave us a lot of things to analyze. I'm not gonna go through all of these, but we had so many analyses done, and it also turns out that because of our nuclear testing that we did in the 50s, we have to recalculate all the carbon-14 results that we get, because it has changed in the atmosphere over time. So we also have to take into consideration when we think that the waste that we have sampled was actually produced. For example, if you have demolition waste from a house, when did this tree build that this house was built of, etc., etc. We found out in the end that about 1/3 of Swedish waste comes from fossil origin, and the EPA, they accepted that. If you are a large combustion facility in Sweden, and don't ask me how they define the large, it's a very gray area, but if you are large, then you have to do testing online and report how much fossil content you have. If you're a smaller combustion site, you can actually use this and say that 1/3 of what I have is fossil. My third example of research that we do is about downtime corrosion in boilers. So dry deposits can absorb moisture from the surrounding air, and that creates a potentially corrosive environment in boilers. And this may occur on different boiler surfaces, such as the furnace walls or the superheaters or the economizers, when the temperature drops under 100 degrees. So it never does in a boiler, right? Yeah, it does, because you turn the boiler off once a year when you're going to do your revision, right? So when it's down for cleaning and maintenance or unplanned shutdowns, there is a risk that you can have corrosion ongoing in the deposits. And depending on what chemical composition the deposits have, it might turn out that the corrosive will accelerate the corrosion in the boiler, so that you will have to turn it off soon again. And when a boiler is down, you lose a lot of money as the owner. So for this particular study, our aim was to investigate the uniform corrosion by measuring corrosion rate and the pitting activity through lab work. So what we did is that we went into boilers directly after they were turned off and had come to a temperature where we could actually go into them, and took deposits, put them in containers and took them directly to our lab, where we mounted them on electrodes that we could measure the corrosion rate with while putting it in a moist environment. We used a few different kinds of steel. This ST45.8 represent un- or low alloyed steels, and you will find that in the boiler walls or in the economizers. We had P91, which represents steels used in the superheaters, and alloy 625, which is a super alloy used for corrosion protection. It's quite expensive, but common in the superheater regions. So what we could see is that for the cheap steel, obviously we had more corrosion. I want you to observe that the y-axis here are different, so you cannot compare them straight off, but quite up to a quite high rate of millimeters per year, up to 1.8. Some pitting activity in the beginning. Pitting corrosion is when it creates a hole straight into, rather than just corroding on the surface. For P91, we could see some corrosion, but not much, and for the expensive alloy, almost nothing at all. But if we look at numbers, you can see that there is always almost a magnitude in between the numbers, depending on which steel you have. This deposit was from the furnace walls, and then we took deposits from the superheaters. For the cheap, we could directly again see a corrosion rate that was quite high, and the pitting activity was extremely high, whereas with a more expensive steel, not as much corrosion activity. So if you would be a boiler owner and you have extremely expensive steel on your superheaters, and you turn your boiler off, where do you clean first? You clean your expensive parts, right? Because you don't want them to wear and tear. Nothing happens there because your steel is good. So what you should do is that you should go to your cheaper parts and clean them first. So this was valuable for the industry in Sweden because they completely turned around their cleaning schedule for the boilers. So we could show that the downtime corrosion increases the fastest within 24 hours, up to 4 days after the deposit has been exposed to the ambient air. And it can have large variation from negligible rates up to 1.8 millimeters per year, depending on which material type that you use. And it also seemed like the presence of chlorine in the deposits affected the corrosion rate more than the presence of other elements. And the initiation of corrosion was dependent on the moisture content, but the corrosion rate wasn't. So the final example I'm going to give you is actually an ongoing study. I mentioned earlier that it's been more and more interesting to look at the metallic aluminum content in fuel that goes to waste combustion. And it's kind of surprising because it's kind of hot when you combust things. So you would expect that metallic aluminum that is small would be oxidized during the combustion. Turns out it's not. So what happens is that we get metallic aluminum in the fly ash. This is 500 microns enlargement, and this is 200 microns enlargement. And you can actually see here aluminum present, although theoretically it shouldn't be there. But it survives through the boiler and ends up in the fly ash. And this is a safety issue because when fly ash is exposed to moisture, it can create hydrogen gas. We've had 2 explosions in Sweden. Luckily, no one has been injured, just material injuries. We had a door that flew 150 meters, so it could have injured someone. There has been at least 2 known explosions in Japan due to hydrogen gas development from fly ash, and there have been fatalities connected to that. So it's a safety issue, but there is also an enormous possibility of energy savings and raw material extraction. There is a lot of energy that is used to reduce aluminum to metallic aluminum. So if we could actually extract it from the fly ash, it would be very good. So what we decided to do was to take the fly ash from bubbling fluidized beds and circulating fluidized beds, because that's where we have seen the most in the fly ash, and see if we could do a mechanical separation to get metallic aluminum powder out, or if maybe we could use it for hydrogen production. What would be the rest after this would be water washed. You would get metals out of that, and you would also be able to wash out salts that could be used for ice prevention on roads. This would be followed by an acidic wash, and then you could possibly use acids from flue gas cleaning or leftovers from any other industry processes. And then you would have the remaining ash to be further treated or landfilled. Today, the water washing and then the acidic wash is something that happens, but we then wanted to add this step. And then I had no more. Yeah, so what we did is that we, in lab scale, tried the hydrogen production. It turns out that it's quite slow, and you need quite a lot of it, and to get it really effective you would have to add other chemicals that would be costly, so it's not economically feasible yet. What we're doing at the moment is that we have looked into a few different ways to mechanically separate it, and we have located a company in Switzerland who thinks that they can do this through electrostatic separation. Everyone else that we talked to said that the particles you have are too small. I know that you're able to see them here, but the majority are actually smaller than 75 microns. So at the moment we have 2 different fly ashes with this company in Switzerland, and I'll be expecting to get the results back by the end of November. And hopefully this will make it possible for us to write up a new proposal and get a pilot plant operating. We did some calculations of the value of the metal in here, and combining all combustion sites in Sweden, we're talking hundreds of thousands of dollars. So I know I'm a little bit over time, but the stage is mine, so I'm going to use it. Some future challenges in waste combustion is obviously the change of the fuel composition owing to the increased recycling of materials. So when you build a boiler, you as the owner will present the manufacturer with a fuel analysis saying this is what my typical fuel will look like. Well, 10 years later it won't look like that, and that's a problem. The overcapacity is something that is beneficial now because we can take in fuel from other countries. It will maybe not be as beneficial when these other countries have figured out how they want to treat their waste in their own countries. We import fuel of other quality. It just happens to be that the quality is better, but it's not what our boilers are designed for. So even if it's better, it can be a problem. Ash handling and recovery of materials from the ashes is getting more and more important. The EPA is on us all the time to do more with the ash and not just landfill it. And there are also political discussions around policy instruments and legislations. The most recent discussion now is about once again adding a tax onto the combustion to get more recyclables out. But when in fact it's not up to the owners of the plants to do the recycling. So the discussion is that this money should be used in getting the recycling industry to actually get more recyclings going. I'm sure there are other challenges. These are the ones that I see as the ones that are most upcoming at the moment. And I think Stan said, but at the moment I live in Toronto in Canada, and I am trying to compare the two different waste management systems that is present in the province of Ontario and Sweden, because Ontario and Sweden are kind of similar when it comes to natural, how it's laid out, and the fact that we have dense cities and rural areas and things like that. And I was, when I started, I came in there and I was like, yay, waste combustion, it's so amazing, why don't you have it? And then after a time, you get like into the political discussion and you realize how cheap landfill is. And it's hard to compete with something that is cheap when your alternative is quite expensive in the beginning as an investment. But anyway, I just want to end with thank you for having me here. And I know I took more time than I was given, but I wanted to say everything I had with me. So thank you for listening. I hope you learned something about Sweden. Don't forget the tacos. And I hope that you learned something about waste combustion and that you'll be interested to maybe go into this area when you choose what you want to do in the future. Thank you very much.
Okay, we have maybe time for just one burning question, and then we'll just
burning question.
That's right. Any burning questions?
Yeah.
What do Swedish people put on their tacos?
It's a good question. So it would be, obviously you can choose, right? But it would be the meat. We normally do our tacos with tortillas, so not the hard shells. It would be a tortilla, and you would have the mince, you would have creme fraiche, you would have a salsa, and then any vegetable that you would like tomatoes, corn, whatever. Yeah.
Okay, let's take Dr. Jones.